reminder, let's say, about what was going on. And so I give you a function of f of x to tell you that that's x plus 5, so that rule is x plus 5. G of x is x squared minus 4x plus 8. And what we're doing in this warm-up is I'm asking you to add the two functions, subtract the two functions in a different order, and then multiply the two functions. So we're doing some polynomial operations as a bit of a warm-up here to this lesson here in chapter 10. So that's kind of the instruction. Y'all get going on it. And I need to send one teeny tiny little email. So I'm going to get this out of the way here. Come on over here. There we go. Hello, James. Who let you in, you dirty dog?
One of the teachers.
That was Mr. Perry. Come on in. I got your warm-up up on the screen there. Ah, put that over there. There now. Much better. We need a little more time, or we got it straight? Feedback. Coach Morgan, I'm finished, or no, more time. Okay, thank you. Y'all have some quiet little church mice this morning. We'll take about 30 more seconds. All right. Even if you're not finished, let's take a gander at this. We are performing some operations with functions. And the first one is to simply add the two together. Should be very straightforward. We've got f of x plus g of x, all right? So Alex, what kind of function is f of x? It's got an x to the first term, so we would call it what? It is a linear function. Andrew, what's g of x?
Quadratic.
It is a quadratic function. So there are going to be some crossovers as far as like terms are concerned. For example, I've got a linear term here and a linear term there. I could combine those two terms using addition. I've got a constant term here and a constant term there. Again, I could combine those two using addition. Similarly, in the second and the third questions, we'll be combining those like terms, but since it's through subtraction, we'll be distributing or changing the signs. One way of looking at this is to say, hey, look, I've got x plus 5 plus x squared minus 4x plus 8. And when we say x squared doesn't have anybody to go with, he just stays as x squared. We got 1x minus 4x, that's minus 3x, and we got 5 plus 8, which last time I checked is 13. Okay, simple enough. We're just adding like terms. We've been doing that since back in August, right? Like term here and here, and that's how we got, for instance, our negative 3x, right? Because we added those together. Now, very similarly, as I mentioned a moment ago, we could take these two, we could, let's see if this works. Oh, of course, Microsoft OneNote wants to be slow. It would have been quicker to daggum write it. There. All right, and the only thing we're going to change now is we're going to change that to a minus sign. So those two, the ones that I highlighted in yellow, for example, they still go together, but I have to change the sign of the second one first. If I say, "Dadgum, Alex, I'm sick of Euro, just get out." You know, y'all heard me say that a million times. I'm not just going to take Alex out. I'm going to distribute this negative times all three of those terms. In other words, I'm going to subtract x squared. I'm going to subtract negative 4x, turning it into a positive 4x, and I'm going to subtract 8. Okay. So let's see here. We got negative x squared, because he doesn't have anybody to go with. He just has that negative distributed upon him. We've got x minus negative 4x, which is going to turn into a what? A positive 5x. Excellent. And then 5 minus 8 is negative 3. Okay. And again, I'll highlight in yellow that linear term is from a combination of x minus negative 4x. That's the small little hiccup that we sometimes see. Now, part 3 is the reverse of that, the opposite of that, because we're going to say, okay, x squared minus 4x plus 8. Now we're going to subtract x plus 5. So we're going to distribute that negative again, but this time into the other function. So what that gives me is a positive x squared. Negative 4x minus 1 more x is going to give me negative 5x. And then 8 minus 5 is positive 3. Lewis, what's the relationship between this answer and this answer? What do you notice about those two? And therefore, those are called opposites. Fellas, A plus B, or excuse me, A minus B and B minus A are always opposites, right? And you can test it out with a simple number check. What's 5 minus 3? What's 3 minus 5? Negative 2. So when we reverse the direction of, or the order of two terms, as we've seen right here in numbers 2 and 3, we've got opposites. And so that's a good observation. Lastly here, check this out. This is a bird of a different color. We're multiplying. We're going to say x plus 5 times x squared minus 4x plus 8. Okay. Now in this case, it's not a FOIL problem, because a FOIL problem will be where we have a binomial times a binomial, right? Joey, how many terms are the result of a FOIL problem? How many products do we have before we simplify? Try again. How many letters are in the word FOIL? 4. So F-O-I-L. And then oftentimes we combine the O and the I, and we have like a trinomial result, right? In this case, Jack McBee, we got a bi times a tri. So how many products are we going to have before simplifying? Well, we're not going to have 4. That's what we would have if there was a bi times a bi. Here I've got a bi times a tri. What's 2 times 3, class? We're going to have 6 products before we simplify. And the idea is that those 6 products, they come about because of the distributive property. X gets multiplied times all 3 of these, and 5 gets multiplied times all 3 of these. So how many little arrows did I just draw? 6. Now there's going to be some that cross over and are like terms. Okay, there will be others that are not like terms. The first multiplication we did was x times x squared, and that's x cubed. For instance, that's the only cubic term. There's no other possible way for me to get a cubic term when I'm multiplying these two guys. But I could get a quadratic term by multiplying x times negative 4x, getting negative 4x squared, and 5 times x squared, getting positive 5x squared. So that tallies up to equal 1x squared. And if you're with it, you can do those in your head. You can do, instead of writing out all 6, you could go ahead and think, beard stroke. How am I going to get a quadratic term as a result? And you would say, well, I could either do it a constant times a quadratic or a linear times a linear. Those are the only 2 ways in this case. Paul?
Wouldn't the first term be 5x cubed?
Why? Okay, so they're individual distributions. Let's go about it this I'll kind of draw it out the long way and you'll see what I mean. And I'll do it in a different color here. All right, so we'll do these top 3 let's delete my first arrows. The top 3 multiplications we'll do in orange. And then the bottom 3 multiplications we'll do in green, okay? So x times x squared, x times negative 4x, and x times 8, right? So that's going to result in 1x cubed minus 4x squared and plus 8x. Everybody see that? Those are my first x times this, x times that, x times that, right? And then in green, I'm going to come back and I'm going to say, oh, okay, well now I'm going to do 5 times x squared. I'm going to do 5 times negative 4x, and I'm going to do 5 times 8, okay? And what does that equal? 5x squared, negative 20x, and 40. And there are my 1, 2, 3, 4, 5, 6 products that we got. And of those 6, what we've just done here in blue is we've said, hey, this one's by himself. There are no more cubic terms. These 2 are both quadratic, and they both therefore come together to make 1x squared. What else could we put together? An 8x and a negative 20x. That adds together to give me what? And then last but not least is 40. Paul, does that make sense?
Yes.
You're very welcome. Now look, when we're doing these, again, I encourage you guys, show as many steps as you need. There are some of you guys that probably could do that distribution in your head, just like there's some of you that can FOIL in your head till the cows come home. And then there's others of us that are like, I do better when I write the FOIL problem out. And that's okay too. Show as much work as you need to. Okay? But all four of these warm-up questions, review, they're called review, right? These are good exam review questions. We have learned how to do this before, so we want to make sure we're not rusty on it moving into next month and kind of wrapping things up. Right? Any questions on your warm-up? Any questions on the review cue that we got starting us off today? All right, then. This section is titled Function Operations and the Inverse of a Function, okay? And so what we're going to be doing is we're going to be messing around with a lot of different functions. And I want to remind you, before we get into the material in earnest here today, I want to remind you what a function is like. I've used this example before. It is like a vending machine, or it's like a factory. It's got things coming into it, and then it performs an operation, and it's got things coming out. You think of a Coke machine, right? You put in money, it does its thing, and then it spits out a Coke, okay? You've got a factory. Let's say it's a tire factory, right? They bring in the raw materials, they do their function operation, and they spit out a tire, okay? Whatever the analogy is that you want. A function has three things. It's got a name, right? It's got the variable that it uses to define its input, right? So X comes in and Y comes out, and it's got some rule that it uses. Maybe this rule is X squared plus 2X minus 3, in which case, as Andrew said a minute ago, maybe that's like a quadratic rule, okay? And so we bring in an X value, you know, and we do our arithmetic, we do our work, and then we spit out a Y value. What do we call, Drew Benton, the set of X values that come in? Starts with a D. Joe, help him out. The domain. Good. The domain is a set of X values. And with particular functions, there are sometimes domain restrictions. Like if this function, for example, let's change it from a quadratic rule to something like this. X over X minus 3. Is there any kind of domain restriction that I'm not allowed to come? It's like, nope, you're not getting in the factory. We don't take your kind around here. Like what number would mess that rule up?
3.
If I tried plugging in a 3 right here comes 3 bebopping along in this conveyor belt, all of a sudden slams into the door because we don't let 3 in because it would mess up the fraction. It would have a denominator of what, class?
0.
A denominator of 0. That's undefined. We have other rules that have domain restrictions, right? You and I have talked before about the almighty square root function. Okay, Charlie, what kind of domain restrictions do we have on that? It's like, man, don't you even try to get in the door. We're not handling negatives around here. We take things from 0 to positive infinity. Okay, so that's our domain. What do we call the set of outputs, George? What do we call the things that, you know, get poofed out the back door here and on down the road? The range. Home on the range, where the deer and the antelope play, where seldom was heard a discouraging word. And the skies are not cloudy all day. Good grief, people. Y'all ever heard that song? Home on the range, where the deer and the antelope play, where seldom is heard a discouraging word, and the skies are not cloudy all day. I can't believe y'all have never heard that daggum song. You've got to be kidding me. Y'all got to get yourselves better educated. All right, let's look at our first example, okay? All right, so I'm giving you over here in red, I'm giving you a couple of what? A couple of quadratic functions, right? Okay, and now I'm asking you to do a division, all right? So in the warm-ups, we did adding, subtracting, and multiplying. Let's try a division one now, okay? So I want to see, as far as function notation goes, this looks like f over g, or we could say f of x over g of x. That's another way of referencing it. The long and short of it here is, fellas, we want to put x squared minus 6x minus 7 over x squared minus 49. Now, you ought to start getting an itch right now. You ought to start getting a little itch. And the only way to scratch that itch is to factor. You ought to look at that blue fraction. You ought to think, ooh, I could factor the top of that. Ooh, I could factor the bottom of that. Why don't you go ahead and try and do that? Factor the top and bottom, because we are at the point now in our mathy preparations. You guys have been taught well enough to know that if you've got a polynomial such as what's on top and on bottom here, if it factors, what in the dump is going on here? If it factors, we might as well factor it out. My OneNote is acting goofy today. That's okay. I'm acting goofy today too. Coach Morgan, you act goofy every day. No, I don't. Shut the heck up. Evan, my math teacher is having conversations with himself. I think he's finally reached his limits. Tiago?
Yes.
Do you have either one of these factored?
Yes.
Which one would you like to tell me about?
That one.
The top one. All right, go for it, bub.
X minus 7.
Beautiful. X minus 7, X plus 1. Who wants to tell me about the bottom one? Oh, if only Quentin would tell me about the bottom one. X minus 7 and X plus 7. Now, you guys might be thinking, what in the world? Where did these guys get that kind of know-how? We've been doing factoring since December. Factoring, the top is just a simple regular trinomial where we look at the constant, find two factors that add up to the linear term. And then, Quentin, you factored out this as a what? What was our factoring technique on this one called? DOS. James? The difference of squares. Good. So it's not only good for us to know how to factor. Obviously, Quentin knows how to factor. We also want to be able to refer to it by its proper name. So that's factoring the difference of two squares. Now, Grove, do you notice anything about our blue fraction there? So what could I do about that? You're telling me this. I'm going to do this. Yeah, like that, right there. I saw the pen moving. He's like, just do that. So we cancel out a common factor. Now, thankfully, and I guess I was moving too quickly to let anybody make this mistake. Thankfully, nobody looked at this first fraction right there as a duh, Coach Morgan, there's an x squared and an x squared. Just cancel that out. Thankfully, nobody did that. You might remember earlier in the year, I said that would earn you a swift kick to the gonads, right? Okay. We don't cancel common terms out because a plus sign and a minus sign, the operators which separate terms, those act as what? Roadblocks. Okay. However, now that we have been able to factor the top and the bottom out, Grove is perfectly within his rights, as are we, to cancel a common factor. To cancel a common factor. So that now this becomes x plus 1 over x plus 7. Okay? So that is the simplified out fraction. But I also ask you, I say, hey, please give the domain. So we're going to revisit that idea of domain restrictions. If this is my function, what is not allowed to get in? Okay, in other words, what is x not allowed to be? Ooh, how now, brown cow? Drew, why'd you say, oh, sorry, Jake, why'd you say plus or minus 7? Very good. Make a note to that effect. That domain restrictions come from the original function, not just the simplified answer, right? Because the original function is written up where there's a quadratic denominator. And how many roots do we know that every quadratic expression has? 2, per our fundamental theorem of algebra, right? So there's 2 roots to that denominator. We factored out and canceled one of them, but that doesn't mean that we have only one domain restriction. Very good, very good. Questions on that example before we move on? All right, again, just kind of operating with some functions here today. Now we're going to get a little crazy, okay? This will be our last example. We've got about 5 minutes left. Y'all might be a little too young to have seen this movie. It's perhaps a wee bit violent, but it's called Inception. Anybody seen the movie Inception? You guys familiar with it? It's a movie by a guy named Christopher Nolan. He's one of my favorite filmmakers. And it stars Leonardo DiCaprio, and it's got several other A-listers, movie stars in it. But the premise is that you put somebody to sleep, and then you hook them up to this machine, and you go to sleep too, and you break into their dreams. Joey, you know what I'm talking about? Okay, so like you break into their dreams to like steal their ideas, right, and steal the things that they know. And so the idea of Inception is he goes on this mission not to steal something from somebody's brain, but to plant something in someone's brain. And so like that's a lot harder. And in the movie you'll learn that, you know, in order to do that, you shouldn't just break into their dream. You should break into their dream, and then in that dream, somebody else falls asleep, and you break into that person's dream. So it's a dream within a dream. And it's like, well, have you ever woken up from a dream and you kind of feel like maybe I'm still asleep? I don't know. Is this real? And that's the whole premise of the movie. And so a dream within a dream is sort of what we're looking at here. This is a function within a function. All right. It's called a composite function. I don't have a baseball bat in here. First period, usually I got a guy that brings in his bat bag, and so I used that as an example the other day. But you know, they make this thing called a composite baseball bat. All right, where it's one material and another material, and it's kind of they're woven together, one inside of another, and that makes for a stronger bond. It makes for a good bat, and that's again the notion of composite here means that we've got a function inside of another function. So let me first ask you this. Let's do a little experiment here. Let's just consider this f function right here, and I want you to tell me what is f of 1. What's f of 1? Good, square root of 6. That's the square root of 1 plus 5, which is the square root of 6. What's f of, what's f of, what do I want? 4. What's f of 4? Good, square root of 4 plus 5, which equals the square root of 9, which you guys know square root of 9 is equal to 3. Okay, so now we're getting a little fancy. What's f of negative 5? Square root of negative 5 plus 5, which equals square root of 0, which equals 0. Okay. What's f of triangle? Very good. Square root of triangle plus 5. I don't know what to do with that, so I'll just stop right there, you know. What's f of spaghetti and meatballs? Yeah, delicious. Deliciosity. That's the square root of spaghetti and meatballs. You know, plus 5. There's your spaghetti and meatballs. Okay. So the rule says whatever's in the parentheses, add 5, take the square root. Add 5, take the square root. Add 5, take the square root. All right. So what if it's f of g? Square root of g plus 5. And that's all you have to think about. Again, what does the rule say? Whatever's in this parentheses, add 5 and take the square root of that. So if g is in the parentheses, we're going to say g plus 5 and then take the square root. And then somebody was taking the next step for me. What do I know g is given in this information? 3 over x. That is a function inside of another function. That's called a composite function. Have y'all seen that in your Algebra 1 classes yet? You guys discussed that any? Okay. That's just pretty typical, you know, Algebra 1 concept or Algebra 1 topic. Let's reverse the order now, okay? So instead of the f function and all of this rigmarole, let's consider the g function. Whoops. So the g function here says, okay, g of 7 would be 3 over 7. G of triangle would be 3 over triangle. G of Coach Morgan would be what? 3 over Coach Morgan. All right. G of F is what? 3 over f. And do we know what f is? So 3 over square root of x plus 5. That's a function inside of another function. Now, this concept of composite functions, you will consider for the next 4.5 years, right? You'll talk about it for a long time because it comes up in Algebra 1 and Algebra 2. It comes up in calculus. So one function inside of another function is totally perfect and fine. You know, I think that would be lovely. You are very kind. Did you go to Kinko's or something?
My husband did it. I don't know why.
Because he's awesome. Tell Tom thank you from me. All right, so the idea of one function inside of another function, right, is very doable. Just remember what the rule says. And whatever this original rule is, we can swap out our x value and put whatever we need to in there. Hey, we're out of time for today, so class is over. We will pick up with more of this tomorrow. I hope you guys have a fantastic day. Be safe, be healthy and happy, and live Jesus in our hearts. All right. Thank you, fellas.